Let's look at the normal vector to a surface. A surface is a 2-parameter object in 3 space. Remember, our goal is to rethink Calc 3, so we're doing things in 3 space, but it's all going to be good for n space. Now let's take a curve on the surface. So we have a composition map, our 1-parameter object in the 2-dimensional parameter space, which then gets taken by the surface parameterization into n space, 3 space here. We're at a particular point. Now we propagate the vectors. Tangent vector in the parameter space goes to tangent vector. Might as well make the unit vector, make life simple. And it gets propagated through the differential into 3 space through the chain rule. So we have our 2 linear maps. Labeling our coordinates. We have this then standard representation in terms of a matrix. I'll use partial symbols here since otherwise too many subscripts. Do the matrix vector multiplication, which of course is matrix composition. There's our first component. Second component, and third component. We'll call this the vector v. The normal vector to the surface should be orthogonal to that. Quick notation change. Our Jacobian, since we don't have a square matrix, here's a new notation for Jacobians for submatrices. So if I take that little 2x2 submatrix, its determinant is given by this symbol. We'll start using this symbol now for square matrices also, when it seems easier. So my normal vector should be orthogonal. Here's my claim. These determinants in each component are my normal vector. In n space, this will be subsumed by the theory of differential forms. My claim is this dot product is 0, so that the vectors are orthogonal. This will define our normal vector. It's a straightforward computation, but you have to group the terms kind of cleverly. So just calculate the dot product. There's the E1 terms. The E2 terms. and the E3 terms. Here's the clever bit. Or think about this 3 by 3 matrix. We're expanding the determinant on the first column. Then my Jacobians are my little submatrices. So there's the first term, the second term, expanding on the y, and then the third term is consistent. Those two columns are the same, so the determinant of that 3 by 3 is 0. And similarly for the next term, except with T2. Expanding on X, T2, there's my submatrix. Expanding on Y, submatrix, and expanding on Z, submatrix. So first and third columns are the same, so the determinant of that 3 by 3 is 0. And there we have it.